what I'm going to do that's different is before I've been focusing on the solution, how to use particles and which way to use it. But I didn't realize until we were talking last night that I need to be able to express what the problem is. What am I trying to solve? Like, what do I think about every day when I work on this? And why has it taken me 20 years to get to this point? So, starting from the beginning, what is the point of the physics library? Why am I in search of that? And it started, I've been designing libraries for years, and they always seem to go wrong. So an analogy that I started realizing why is version 1 was always my best, because if you want to design a castle and I build a perfect Lego set with 10 pieces, in version 1 I can put it together and you can build a castle and the walls, and I'm a hero. It's a great library. In version 2, somebody comes to me and says, I want to build a boat. And I have a perfect Lego set, but I need a rope, rudder, and a sail. And I have these exceptions to the rule, not too bad. In version 3, somebody wants to build a car with my library. And now I have a perfect Lego set with a rope, a rudder, a sail, a windshield, steering wheel, tires, and all these exceptions to the rule. And what was a great library for building castles with these 10 Lego sets becomes a pain in the ass to use. So by version 4, I'm rethinking it and scrapping it and starting over. And it's pretty much an industry trend. None of these software and libraries last too long. 5, 7 years from now, whatever we're doing is going to be gone and there'll be the next great idea. And so I began thinking about, well, how does it work in the real world? We have these laws of physics. We have protons, neutrons, electrons, and they're always consistent with each other. There's no exceptions to the rule. The rule is consistent. We can build houses and we can build cars. We can build castles and we can build boats. But it's the same Lego set. So I started realizing what I'm doing wrong is I keep trying to invent my own universe. My framework, my libraries, the operating system, the language, is I'm picking the universe that I want to live in and inventing it as I go along, and I'm just not as smart as the universe. So I realized that the laws of physics are out there already. This has been figured out. We can build everything in the universe. So in theory, using these same parts, I should be able to build everything in the virtual world. So all I have to do is figure out what components in physics match with programming.
What's the actual library in reality?
What is the actual library in reality? And then how do I use it? The first problem that I have had and continue to have is I can build a library that represents physics and be somewhat authentic, but it doesn't mean I know how to use it. It's like building a fighter plane in your garage, but it doesn't mean you know how to fly. So I have this library of parts, protons, neutrons, electrons. How do I use it to write a program? So I'm going to take us through many of my failures. And I think it'll help understand why this is, an important project, and, why it's taken 20 years and why we're still not done, because it's a very hard problem to solve. And I'm going to take you through the way I've thought about it over the years and my changing point of view to get to where it is now. And I think that'll help. If you can understand what I'm thinking about, you can understand the problem.
It helped me better conceptualize some things in physics that were a little less clear for me. Like just last night, I'm like, that makes a lot of sense. I can conceptualize that, and it helped me reinterpolate back to a more abstract concept that was more foggy for me. So thank you.
Yeah, so we'll start with, okay, so our goal is we're going to build software the way the rest of the universe works and the way we build everything else. So, we start at the basics. Let's just say we have protons, neutrons, electrons, And these things are broken into quarks. We have gluons. We have gravity, photons. We also have space. And this list can start getting pretty extensive because things come together. We now have atoms. We have molecules, compounds. We have kinds of bindings, covalent bonds, ionic bonds, covalent, I think that's how you spell it, ionic. We even have alloys. And the list goes on. In chemistry, along with compounds, we now have polymers. And so, but we'll start with just this and say, okay, we need to map this into programming. So what do we have in programming? Not really a lot. We have if statements, while loops, functions, classes, interfaces, instances or objects. So let's try to map them. Well, looking at this doesn't look too easy to map. What am I going to say? A quark is an if statement? All right, let's go with that. We'll use quarks to represent if statements, and we'll use gluons for while loops. But then how do they interact with each other? Quarks go together with gluons, so if and while statements, whiles have conditions. I can kind of see that. But what about functions? What's a function? Maybe it holds code together. Maybe we use gravity over here. As you start looking at this, it turns out it's not that easy. Because now all of a sudden, these things have to start behaving the way the laws of physics would dictate. So pretty quickly in the first day trying to tie this together, it's going to be, this isn't even going to work. This isn't going to look like physics. This is going to turn into a mess really quickly. I need to think about computers and programming differently. I can't just do a mapping. That won't work. So suppose I think about it in terms of maybe space and time. Why don't I look at it from a dimensional point of view? I can say, okay, let's start with space. You have computer memory. I can tie space to computer memory. Well, that seems like a pretty good insight. It seems like where it belongs. So and if I assume that in programming every class or variable takes up space, so I should be able to map my memory usage to space and manage space independently. So now I have to manage my own memory, and I have, variables in memory. And pretty quickly as I think about it, it's like, okay, I'll write some code and manage my own memory and create classes that point to space. So at least I can get one dimension right. But then space has properties in it, like you're creating memory and freeing memory. What's doing that? Space isn't allocating itself and freeing itself. I have some kind of a class or a function that creates a variable that's pointing into space, but this variable goes out of scope and this thing disappears and something's cleaning it up. What's doing that? Quarks? Gravity? What's freeing my memory? So I can work on this and play around with it, but pretty soon I'm inventing my own laws of physics. Pretty soon I'm saying, I have a quark that just comes and erases this chunk of memory. And that doesn't look like the laws of physics. This is the wrong way to think about it. I can't think about programming in terms of a single dimension and try to slice it up. And I've tried it with time. Suppose we do it with the time dimension. Say, all right, forget this space for a minute. There goes a month of code I just threw out. This isn't going anywhere. We have the system clock, and we can set, like, with event handling, everything is some kind of time event. And all the code, normally we execute it sequentially from beginning to end. Suppose I slice all my code up and into all kinds of event handling, like things that update the screen, things that write to the server, things that read the database. It's just it's sliced up, and I organize them, and things kind of execute in slices. I can experiment with that, but that's not going to work out too good either, because things are not going to happen in the order I expect them to happen, and I'm just making a mess of my program. So I'm stuck again. So this isn't going to work. So there's another couple of months of playing around with it and getting nowhere. So there's another way that I can think of. Let's start from the other way. Instead of looking at the program, let's look at what we got and say these are the patterns. So let's pick one, gravity. What is gravity in a program? We know that we have galaxies, but, galaxies that have X. We have stars. Let's start with our sun, actually. Galaxies contain stars, but we have the sun, and then we have these orbitals, planets. And then we have moons. If we start by looking from the point of view of physics, and let's just call this, governed by gravity. Where have I seen this before in a program? Does it look familiar?
Not a program, but it kind of looks familiar.
Looks familiar, right? Suppose we have a server over here, which is the center. Planets are like user sessions and logins. They're independent from each other, but they orbit the server. Moons are one or more processes that may run independent of each other within a user session. It's kind of does look familiar. Can we think of programming in terms of gravitational fields, where you have different scope? Another planet over here, it may have very limited impact. They're pretty far away. They don't really impact each other, but they definitely have something in common. There's a center of gravity where these things are being pulled to. They're completely independent. Their variables and scoping is completely independent. Maybe that's gravity. So, okay, that's something to register. What about atoms? We have atoms. They have protons and neutrons, and they have electrons orbiting. Does that look familiar? Where have I seen that before in programming? It's like, well, protons have charge, plus and minus. Could that be if-else? What else could it be? Atoms can come together and create molecules. Where have I seen that before? Like records. Records are pieces that come together. And you have name, address, city, state, zip. It looks a little bit like a compound if you can say that the atoms are variables. And it's like, okay, atoms are variables. Let's say we do that. So now they're made up of protons and neutrons. Where do we put the variables? Let's just say we say a neutron's a good place to store a variable. It doesn't really explain in the laws of physics, like, if a neutron is a 10 and sometimes it's a 20 and sometimes it's a 30, our neutrons don't look like pool balls with numbers written on them. So we have a problem there. How do we map it? Where is the value? This has been something that's taken, I think, Thad, you figured it out, but it's taken me 20 years that I figured this will always be a flaw in my physics library, because I'm going to take the laws of physics, even if I'm perfect in every other way, I'm just going to make protons and neutrons like pool balls, and they're going to have numbers written on them. And I know that's not real, but it's the best I can do. But looking at that, let's say I decide that neutrons are going to have the values. So now I'm making atoms, building them into compounds, and I'm using electrons in some way to bind these things together. But as I start binding them together, I want to write a program using this. Can I really use it? So I start working on it. But then I end up, the electrons are binding with neutrons. And I get these neutron-electron pairs. It's like I think I made a mistake somewhere because I'm changing the laws of physics. It was close, a lot better than the other crap that I've been doing over the past couple of years. I've written a lot of stuff using it, but there's some hokiness in there. And it's like I'm trying to test some other patterns using this. So you know what? I'm going to continue. I know it's wrong. I'm going to continue using neutrons to store values that bind with electrons to get things done. I'm going to have to rewrite this library later. And I test some ideas, and it gets a little further along, but I realize my universe is getting more and more distorted as I go on. I have these neutron-electron pairs, and all these other things just aren't working the way they really do. But if you put it in a proton, say the value is here, and start changing all the code around along with many other things. My original version, I didn't even break it down to protons and neutrons. I just said atoms have values. And I just ignored what happened below, because you have a lot going on. Like if I have a value in an atom, what's going on in the protons? What is going on in the quarks? We have up and down quarks, and like many different kinds of quarks. And then there's gluons. So like, how does that fit into the picture? I'm a long way from if, then, while, classes and objects. It's where do all these things fit? But the one thing I did notice is when I have protons as values, it kind of worked pretty well. It started allowing me to think of a program in terms of electronics. In theory, if this is really using the laws of physics, I can write a program from the point of view of electronics. I can make transistors. I can make diodes. Where would a diode be used in a program? How does that look familiar? Well, how about conductors, capacitors? Like, have we seen that behavior in a program somewhere before? In theory, if I'm doing this, if I did get it right, if that's where the value is stored, I should be able to do some at least rudimentary electronics. If I can't get the basics of electronics to work, then I probably didn't get it right. And maybe values are stored in photons. That's a good place to look. Photons have frequency. Maybe that's where the numbers are, right? Because you can have an infinite range of frequencies with photons. You can store all kinds of numbers in photons, and I've gone down that path before, and it was partially right. I do use photons for carrying values now, but I used to use photons for everything. The problem is photons don't have mass. There's a lot of things that you can't use them in chemical reactions. So if you have all your values in photons, which is great, I can make a good library, but I start distorting the laws of physics when I try to do chemistry. It's like all these photons are combining in electrical ways, and it doesn't make any sense. So all the values can't be stored in the photon. So it's a lot of almost trial and error to map physics and programming. But let's go with this. We do have something. Can we make diodes with this? Like, if we can't do anything in electrons, then I probably got it wrong. But where have I seen? Let's just start with let's start with the diode. Basically, current can flow one direction but can't go back. Have I ever seen that behavior in a program before? It's like, yeah, I think I have. I've seen that before. How about data binding? You have a field on the screen, person's name, and you have a memory record, an address record, that has name, address, city, state, and zip. And this is the name field. People type in it. And we want this value to go here, to this variable. And then later we have a save operation. And we save it. So this looks like one-way data binding. If I put a diode here, then the data will flow one way, but it can't go back. What if I want it to go two ways? If I read the record from the database and I wanted to update the screen, and I want them to enter in the screen and go back. Well, in that case, what if I make this a conductor? Now it can flow either directions, but for whatever reason, they can change their name, but they're not allowed to change the zip. That's done by the accounting department. So we put a diode here going this way. And you have the zip code field that reads out of a database, but you can't change it. And if you do, it won't flow back because it's going through a diode. So it's like, that's not too bad. You know, it's like, I'm starting to see electrical properties that I can use on these variables. It's starting to look a little bit like physics, and I can I'm seeing something come out. But can I do chemistry with that? Because this should not only have electrical properties, it should also have chemical properties. Does it look like chemistry? Well, if I have a bunch of atoms if I create a compound, which is this address record, and each of these are atoms, that looks familiar too. Address records, what we think of an address record, is a compound that contains a list of atoms. It's like, I can work with that. But what about databases? You have rows of address records. Well, we can create polymers. Polymers are really complex molecules that have repeating parts to them. And it's like, this is starting to look like chemistry. We have polymers. And rows of address records that you can query the database do look like chemistry. So this is getting pretty far. I have values in protons. It ignores the quarks. I know that it's not complete, but I'm making progress. I now have something that I can use electronic circuits on if I want to design things with circuits, or if I want to use chemical reactions on it, I can do both. So it seems like it's in the right direction. So let's go and look at the list. We now kind of found a use for atoms. We found a use for protons. I haven't spoken too much about the electrons, but I'll get to that. We have electrical flow. I haven't done the quarks, gluons. I think I have a place for gravity. Photons, I know what I can't do with them, because if I store values in photons, chemistry falls apart. I've made that mistake. Space, I'm not too sure of yet. Where does space fit? Where is space? It's kind of a three-dimensional view in programming. Where does that fit in programming? Like, I got it wrong before when I just thought of the memory from 0 to however much memory you have as a one-dimensional thing that I'm storing things in. That didn't work. Is there another place that space could be hiding in a program? And let me actually get to that before I even go to the quarks. Where does space exist in a program? After a lot of trial and error and thinking about it different ways, I'm thinking about structure. Okay, let's say we have this address record, which is a compound, and it has atoms. Another atom, another atom. And these atoms point or contain quarks. And these compounds are arranged in polymers as lists of compounds. It looks, something is holding these things together. They're related to each other. And it kind of has a dimensional aspect to it. A little different than gravity, because gravity is kind of holding things together with scopes, with separate scopes. Things are orbiting common points. But then, and they're independently bound. Or not bound, like different planets have no relationship to each other. But here, in the compounds, we have atoms that tie together, and the program itself has kind of a 3 or more dimensional structure. When you think about code, you have a class that's containing atoms that inherit from particles, and you start looking at the whole structure of the program. It's taking a shape like this room. This room has, a kitchen, it has a refrigerator, it has like all these breakages where things point in different ways, but ultimately together, this house is bound together tightly. It's not really governed necessarily by the force of gravity. I mean, basically, it has to be strong enough to resist gravity, but it has space. So I began looking at programs, the actual programming structure of the way things are held together as the dimension of space. Not necessarily the memory, as a patch of memory, but actually the code itself is structured and has dimension. If we go down to the protons, and now we have quarks. And I forgot if the proton is 2 up quarks and the down, and the neutron is the other way around. But it doesn't really matter for now. And neutrons are 2 down quarks, down and down. I think that's right, but maybe it's reversed. Where have I seen that before in programs? How could that be useful? I know I kind of got it right when I put the value with the proton. But is it in the down quark? Is that where the value is stored? But then what do I do with these 2 up quarks? If they exist in physics, they should exist in programming somewhere. Or do I put the value here, but then is this a null up quark? Am I defining my own universe again? Like, it's all right, I'll use the up quark for this and the down quark for that, and I'll ignore this one. It's like I can get pretty far. I can still get electronics to work. I can get a lot of chemistry to work. Chemistry doesn't care, if the value is stored here or here. So I can tweak my universe a little bit, but I know it's wrong. So there must be a place where these 2 quarks are meaningful. Well, one problem, and Version 1.0 of Angular had this problem with two-way data binding. If you get a database record name and you want to bind it to a variable in the screen, the person's name, and you want it to go someplace else, maybe you're going to update the title of the form or something, and the person's name is up here, and you do two-way data binding like this, and you want to do two-way data binding like that, and whenever the name changes, you want to update that, and the original name is Joe, and now you change it to Bob, and it goes here, and this changes to Bob, and this changes to Bob, and then this comes down, sends a change to Bob here, and that sends a change Bob, and eventually you end up in an infinite loop that's hard to resolve. So two-way data binding is a hard thing to do in programming, and you could end up with infinite loops because how do you know when you're done? And I remember in the older version of Angular, what they did is if they came around 10 times or more, it would throw an error and you'd have to look at it, and maybe you can solve it by not, you bind it this way, but now you have programming bugs. Can we do better than that? And can Quarks help us with that? Well, I think we can. If we say we'll use these up quarks for the value, so now it has Joe and Joe. And when a value changes, this one turns to Bob, and it compares with the other quark, and if this quark is Joe, it makes the change Bob, and we'll get to the rest of the circuit to notify the next thing. A change happens so it can notify the next thing that also has two quarks. But at some point when it comes back and says Bob, if you're going in an infinite loop, it'll compare to the second quark, I'm already Bob. The transition already happened. And we can keep track of, in the down quark, for example, that we're in a state of transition and now we've settled. So basically there's switches in the variables that it can say, okay, I've already done my thing, I won't notify anyone because effectively I've already done that and I haven't made a change. So we can fix that problem of two-way data binding using the quarks, that the proton has the value, but the quarks kind of have to settle down for a value to stick. Like if there's a change, it's like a vibration almost. They're kind of shaking themselves out, and then they get back to a steady state. That kind of does look like physics. There's, not bad. But we also have these things like gluons and color charges. Like, where have I seen that before? Gluons, and then, you have red, blue, green, and anti-red, anti-blue, anti-green. It's like, huh? And they're constantly changing. Have I ever seen something like that before in the laws of physics, or in programming? That's been a hard one for a long time. No, never. Programs don't have changing values that change, as they exist. They don't change. So, all right, we'll ignore this from the library for a while. But there's always a nagging thing. There's something familiar about that. Where have I seen this before? Well, I'll get to the photons, but if you say red is the actual value, you have a value called, 100.07. That's the value. But there's also the formatted version of it, string 100.07. And you also have the photon compressed version, which I haven't talked about, but I found a place for photons. There are different ways which would have a length field. Like this value is storing 1, 2, 3, 4, 5 digits, and then a compressed value of this in here for transmitting. So in a sense, the values are changing colors all the time. It depends if you put it on the screen, if you send it over the wire, if you add to it.
They have three different expressions.
They have three different expressions.
Each of them will lead you to the same thing.
It'll lead to the same thing. It's just three different expressions of the same thing. But the thing is, they don't just transform for nothing. Like, this didn't just go from here to here without some code putting a dollar sign in front of it and turning it into a string. So, it's still not quite physics, because now I just turned red into blue and I wrote some code to do that. But is that code just floating out in infinity and just pops in and turns my red to a blue, and then goes away? Where have I seen that before? Actually, I have seen random code appear out of nowhere, make a transformation, and disappear again. And it's like, nailed it. Now I know where the code to make it's the anti-version of itself that does the transformation. So now we have these three different expressions, which is really all we need to be able to display it on a screen, write it into a database, transmit it over a wire. This is starting to look like the behaviors of physics. Now I can do electronics. I don't have this uneasy feeling that I'm not sure where things are. So I think we kind of nailed quarks and gluons. The photons that I'll come to, photons are kind of interesting things because at the speed of light, time stops. And the one thing, we do have time, because time exists in a program because it's a clock cycle. Everything's, as long as the timer and the clock keeps running, the program keeps running. If you stop the clock, the program halts in memory. It pretty much ceased to exist. There is no program if there is no time. And so, okay, I think we know where that goes, and we don't really have to do anything specifically for it. Later, I'll come back to that because there is elements of time in multiprocessing, right? And that was another big one. Where is energy in a program? And actually, before I get to the photons, I'll talk about where does energy, that seems familiar too. And without the clock executing, in a sense, the motion of the program requires energy. So the different processors, you can run things in parallel on different processors, but you can think of that as your thread management is classes of energy. You know, when I want to create a thread, I'm really executing energy. And the chip heats up, coincidentally. As I run multiple threads and do all these processors, the chip is heating up. And it's like, that probably is a very good way to think about energy. The mere fact that the chip is heating up while this code is running. I think I nailed energy there. But the photons, they transmit themselves. They're the smallest possible particle, the fastest possible particle, but they're not influenced by time. So where the hell do they exist? Well, where have I seen a photon behavior in a program before? Seems familiar. Let's say I have a server here and like a client browser or some application. Let's just call this a browser. And this thing is running on its own computer with its own clock, which means it has time. The server has time. But we expect time to stop in a photon because it's moving at the speed of light. Well, where have I seen that before? Browsers talk to servers. The messages, like radiation, radiate out. This is a message going to here. Once that message is sent from the server, it's no longer governed by the time of the server nor of the browser.
Light comes from the sun.
Light comes from the sun. And everything's being absorbed and can be emitted. Photons can be emitted. I'm not cheating the laws of physics. Actually, atoms under certain interactions will emit photons. Atoms have charge. They have the value. And they can emit that. And when it's emitted between machines, time stops. It's the fastest possible representation. When, I alluded to it with one of the expressions of a value is a very highly compressed value, which is the photon version. So if I have something like 100.07 with an implied decimal point, which I can talk later, I put a length code of 5, but I compress this. I'm using base 52, which is, another story, not 64, like most people do. So this would have 1 byte for a 5, and this would be compressed. Actually, this would be compressed into 1 byte in base 52. So this is a very tiny message going across. It's moving very fast because it's the smallest representation of this value that you can really get. It's compressed. It's like, I think I found my photons. It's not governed by time, moves really fast, is super small. So my messaging is done by photons, and any atom or molecule can emit photons. So now I can have an address record, and I can safely add an emit function, and the emit function on the molecule will go to each of its atoms in the list and fire off emit. And we use the color charge to actually get the photon value, and now it emits. So I can emit an address record in the smallest compressed form out to another machine.
So by using those 3 different color charges with the 2 different states they might be in, you can, at least from a coding perspective, help to maximize the compression of information that when being transferred from a server to a client or a client to a server, effectively from its observational standpoint, experiences no time.
It experiences no time. 99% of the time, I'm taking physics and trying to fit it into programming. But every now and then, it's like, this could go the other way. When one thing that this is telling me, if this is right, then the quarks and the color charges actually do have something to do with photon emissions. Because there is some transformation at that really low level. And, it's not that color is color in frequency of light, because color is kind of an arbitrary thing, but it might actually have to do something with photon emissions. It's going through this color, anti-color, these transformations. And we know atoms can emit photons. Like, where the hell is that coming from? And going from the programming point of view back to physics, that might give a clue that actually color charge may effectively have color. Like, it may actually be that there's something going on there. And, one thing that I would add is as I've worked on this library, I've never been concerned with why. I've been curious about why. Like right now, this kind of raises kind of an interesting question. Like, that's kind of interesting. I've more been concerned about how. I never really, I'd look on Wikipedia and find the behavior of protons, and it contains quarks, and okay, smarter people than me figured that out. This is how it works. I'm not going to question why. How can I use this as a Lego set in the virtual world? And ultimately, I'd like to put the why in there. And I'll come back to neutrons, and you'll see why Y starts becoming important. But I think we may have gotten photons and we may have gotten space. Neutrinos and neutrons I left out. I think we got molecules. The only difference between molecules and atoms is typically in programming, you have lists of with different type things, like a compound. If you have an integer, a string, a Boolean, a date, these are all different kinds of atoms. So you would consider that a compound, like a molecule would be O2, H2 of the same type. We also have lists of people's names that are all the same type. So you can think of that as a molecule, a list of everybody's name. It's all name atoms, it's all strings. But an address record would be a compound because the zip code is probably a number and it's like a different type, right? And, we can get back into building higher protons and how they build up. But let me get back to, so I think we got this. The different types of bonds it's continuing to work because I'm changing my library and I'm not sure if I got them right. We need to think about this more. Alloys are interesting things. You can be blending certain types of, like if you think of it in a database, a table join is kind of creating an alloy. But I'm still experimenting with that. I haven't fully figured that out, but if you're joining people's names, let's say you have an employee number and a person's name, and you have a separate address for the person that has the same ID as their name, and you join them together, and now you get the person's name, address, city, state, zip, and other properties. You're kind of making alloys.
Similar molecules and compounds coming together in a particular way that form basically a new structure, so to speak.
Form a new structure. And when you have rows, you have polymers. Now, the thing that polymers are interesting things. You have one molecule that may have some behavior, but when you string them all together and create polymers out of it, they create whole new behaviors. And I found within polymers, I can write, if the behavior I put in there, I can put kind of query and selection code in there that polymers have their own behavior. And I notice miraculously, as I create polymers of records, I can do certain kinds of activities like catalysts and things other that interact with it, that make a transformation. Maybe I can order them, sort them, they can break up. In nature, chemistry, things come together and break apart all the time. I can have catalysts that maybe out of this polymer of name and address records, I only want an ordered list of zip codes. I can have a catalyst that'll break apart this whole chemical thing and leave an ordered list of zip codes, which is just atoms. It's like lighting things on fire or whatever. These transformations happen all the time in chemistry. So with polymers, now I can build in certain behaviors and catalysts that I know of, and this would be somebody who knows a lot about chemistry, who wants to think about programming chemical reactions. Would be fantastic if somebody was really interested. My knowledge of chemistry isn't as good as physics, so somebody could be thinking about that. But that's the direction, and I think that what we have here supports that. I think we can do things like this. I've done limited amounts. I'm not sure if I got it right.
As you get it more and more right, I'm seeing, and as we get ours more and more right, you should be able to find equations on the list that do some of the functions you're needing done, right? They should have, if you write out the equation and we can symbolically represent the equation, then we'll see the algebra represented. We'll find something else that has that algebra. And then we can literally have the thing and the scale of the thing that's doing the same transform.
And actually, that's almost where I'm going next.
Really?
Literally where the math starts to fit in and why it's important and why just stopping at how things work. The links are like incredible,
We're totally going to figure this out.
Yeah, we're going to figure this out. I figured out where neutrons are, and like I talked about the atoms, they have values in the protons. Right now we're dealing with one proton, so we're talking about hydrogen. I'll get to helium and lithium and the other ones. But sometimes there are neutrons and sometimes there's not. Where have I seen that in programming before? How could that be useful? That was kind of a tough one. But you can think of, if this is a hydrogen atom, it can be very light. It could be a proton, an electron, nothing more. But it could also have these extra neutrons that are heavier. So what would that be? Well, what about the history, a past value? If this has the value of Joe and I change it to Bob, but I want to create an isotope of hydrogen, I can put Joe in the neutron and put the new value Bob here. All it's doing is making this atom heavier. I'm carrying a little baggage, but that's what happens in physics. You add some neutrons, it gets heavier. So, okay, Joe has the previous value. It's neutral. It's not going to interfere with any chemical reaction, so I can still do catalytic reactions on this thing, and it's carrying its past value around.
It gains an ability to stop an infinite loop on itself.
That's another way. It's being, right now I'm doing it in the quarks, but it could actually be done with this. But what I'm using this for is, you have a form on the screen. Has name, address, city, state, zip. And sometimes you'll see like a reset button. Somebody's filling out a form and they just want to reset the values and have it go back to what it was before. They made a mistake. They're filling out the billing address and they thought they were filling out the shipping address, and like, oops, I did it wrong. Let me reset this. Well, in typical programming, I have to have another copy of this record. They start changing this and they hit reset, and I'm like, oops, I gotta write some code, take the previous value that I had, copy it all back, delete that value, go back. It's a decent amount of work for a simple thing. Well, what if all these atoms became isotopes and they had the previous value? Now I can do a decay. If I do a neutron decay, what comes out of it? A proton, an electron, and a neutrino. Well, what do I want? I want a proton. So now they hit reset. I go to this atom and let it reset itself, decay. The atom decays, all the neutrons become protons again, the neutrons fly, well, they decay. And so Bob disappears, Joe comes back. Now I can kind of almost run programs in reverse, and very easily with a single button click, I can go to my atom and say decay all the atoms, which goes all the way down to each of the neutrons. They decay back to protons, and blip. And now I have the data binding, maybe with the diodes or conductors, and all these values just change right back on the screen. So if you ask, why do I continue working on this, is as many times as I've gotten this wrong and had to scrap it and start over again, I did realize that the closer I get to the laws of physics, the more powerful a programming library it becomes. And that's why I can't quit. It's like, there's something to this. What this is allowing me to do is true software engineering governed by the laws of physics. I don't see, we call ourselves software engineers, but we're not equivalent to chemical and electrical engineers who are governed by the laws of physics, and they're actually engineering something that we all agree on. In software, there's nothing we agree on. Everything we use is a new universe. So I've been finding that as these things start coming together, the closer it gets to the laws of physics, the more powerful it becomes. And here we start seeing things. Now we can have catalysts do chemical reactions on these things, and we end up with one library everywhere. I've used these libraries, different versions of it, to do graphics programming, to write, B-tree type databases, to write custom servers from scratch, socket programming. I'm not using Angular and then using React and Spring Boot on the server and, Jackson parser for JSON, and the list goes on and on. I'm using the same library on the server, on the client, in the database. At this moment, I'm starting to wonder, You know, when values are stored in a database, where does that seem familiar? When it's stored in a database, time is kind of squeezed out. Doesn't seem to be even any energy going on. It's just dense matter. You know, where have I seen that before? And it's like, looks like a black hole. A database is kind of like a black hole of compressed matter that just compresses down. But it does have structure. I can kind of say it doesn't have time. Well, that matches to the laws of physics right there. You know, like a database and black hole mappings seem pretty realistic. The jury is out on that, but that's where I'm leaning. Databases, and then thinking the reverse, that would mean that black holes must have structure, don't have time. They wouldn't have space either, because if space is defined as the structure of these things running and interacting with each other, that's not a database either. So it seems like black holes wouldn't have space. Space would be collapsed out of it and time would be collapsed out of it. But they would have structure of, since there's data there and data is values and charge, there must be something going on in black holes. They're not just completely dense and black. But that's conjecture, thinking back from programming, going backwards. There was some other point that I wanted to make about where the math ties into this. The one thing, I've kind of been cheating all along because I don't know why things happen. A neutron is a neutron, and a neutron decays. So I can write a function called decay. And what it does is it takes the value that's stored in the neutron, puts it in, creates a new proton, creates a new electron, and creates a neutrino. And that's what I return. I return this value. And I do decay, but I don't know why any of this happens. I can't make it happen. There's no math in there. I just say that happens. Well, if I look at this, if I have some mathematical formula that I can execute that would do the transformation, it would be more realistic, right? And I can eventually, one thing I can't do at my library right now is I can't set it free to run kind of like neural networks, where they kind of run on their own and self-learn and self-train, and like the game of life. I want to be able to take these atoms and chemicals and put it in a computer and run it and just see what happens. But the problem is, these are hard classes. These have structure. Atoms, protons are hard things. So I have to put these hacks in here to turn a neutron into a proton. But if we actually had the transformational mathematics, and these weren't hardened structures, they were more objects that had properties and behaviors, but they weren't things. I'm still treating everything like hardened particles. But if they weren't things, it's okay for them to have properties and behavior, but not be a thing. Now they can transform one into another. And here's another place, the neutrino that gets released. Even when I do this transform, this is another case where the neutrino looks like physics, where I'm having the same problem. You know, at first I was thinking, what the hell is in a neutrino? What can I use a neutrino for in programming? Like, what does it remind me of? And like, I was thinking they're useless. They have no charge. They have no value. They're practically moving at the speed of light. They don't interact with anything. What the hell is a neutrino, and how could I possibly use that in programs? And as I was thinking about it and going, does it look like data? Does it look like memory? Does it look like time? Like, what the hell is a neutrino? Like, all the information is squeezed out of it, and it can't interact with anything. Neutrinos are just nothing. But then I started thinking about, actually, there is information in a neutrino. Neutrinos travel in straight lines from their inception. So they act like pointers. They do carry something. You know where they came from. If you knew the trajectory, If you can measure a neutrino, then you would know at least where it came from. And there's some information, so it's not lost. But now I have the same problem in my programming libraries, having the law in physics. Okay, I'm going to put a pointer in here. Use neutrinos for my pointers. Sounds like a great idea. Now I can point to anything, anywhere. The problem is I have no way to detect it. If I have an atom and I put a function called detect neutrino to get the value or get a pointer, it's like, well, that's fake physics. I can't do that. I'm cheating. So it's like, now I have the same problem with the neutrinos in programming that we have in physics, which makes me believe I'm probably on the right track if I'm having the same problem. If I have to make something up to use it. So I've been finding over the years, 90% of the time I'm going this way. I'm doing physics and building programs. But every now and then there's a few gems in there where it's like, wow, I have the same problem in programming that we have in physics. There must be something similar about these. So the ultimate goal of this is twofold. If we can put the Y in here, when I do neutron decay and it actually becomes a proton, and I can actually have a computer run things on its own like neurons, it has all its behavior and it's just, now we have a simulator. And with that simulator, what could we do with it? Well, we have CERN that's smashing atoms together at nearly the speed of light and spending billions of dollars on this. But they don't smash things together at 45-degree angles, at 90-degree angles. We could do that in a simulator. We can actually simulate this in software if we get the math right. So for one thing, we can build amazing simulations and figure out chemistry. We can figure like all kinds of stuff, make new alloys that we didn't expect, light, who knows what's going to come out, right? If we only have the properties and behaviors and the actual math does the interactions, then I won't necessarily have an atom and a proton and neutron. I won't have these particles anymore. What I'll really have is basically, or I guess maybe I'll have one particle object that has math executing in it and takes on the behavior of a proton or a neutron, but it is not a proton or a neutron. It's just a particle that has behaviors and properties that emerge and disappear. That would lead us to being able to build simulators. I also believe that this version of the library, which is really powerful, even though it's somewhat rigid, I have like rigid point particles that I'm using, I can build amazing programs with that. But what would I be able to build if I didn't have those rigid point particles? And now programs can run and really solve problems in realistic ways. That's kind of the goal of the library.
So the closer we actually get with the library to modeling our reality, the better we can help to model reality.
The better we can model reality. And so far it's proven out, the closer it gets to the actual laws of physics, the better able it is to program virtual software.
So your construction so far, though, isn't to try to, on a higher order, make a construction that mimics nature. You're trying to actually use the things in nature that software needs directly. Right?
Directly.
So if you do pull that off, how is it virtual? Or how is anything not virtual? It becomes exactly the same as the things we're calling real.
It becomes a running universe.
Yeah.
And is it virtual?
When you understand it that well, you should be able to construct any form you want. And that's literally the machine you're talking about is a computer that is the replicator. It's the computer that actually builds and makes the transforms and puts things together right.
Yeah, because it happens in the real world. It has to be able to happen in the virtual.
Purpose,
On purpose. It has to be able to happen.
Sounds like such a leap at this point in history, but it's not.
Yeah, and also the thought of giving respect to the title software engineer, that we are now on par with everyone else in the engineering world. Because right now, the title software engineer is kind of a joke.
It changes the game too, because it forces everybody to a fundamental language, right? You get to start with the language that's the most universal to begin with and build everything with its ingredients. But people spend their focus on learning that language together, and when we're all communicating the same language in the coding world, we can say a lot more.
We can say a lot more, and we have a common terminology. You know, if you're a React programmer and I'm an Angular programmer, we have two different definitions of what a module means and what components mean, and we don't even understand each other as programmers because we're all speaking different languages. If all software was built out of this, you'll know what I'm talking about when I say let's store this in neutrons. It's like,
and you'll never beat that action, right? You won't be able to program a thing that can do it better than the way physics does it.
Right. That comes to your version 1.infinity. If we get it right, then there will be no version 2. This is, you know, I think it'll be a long time to get it right. I think this requires a lot of people wanting to think like this. And focusing on it. You know, there's chemistry, and then we can get up to biology and the formation of DNA, and like this has so much more. Full electronics. You know, where does electronics appear like in programming? There's so many places where we would want to use diodes and transistors and things. There are times that I want to think about programs in terms of event handling and nervous system. And I've done some rudimentary event handling with neurons. But imagine if neural networks were actually built on top of a physics library that is self-running chemistry. What would the neural network now be able to do?
We're using the code inherent in nature to help model the things that we're interacting with. And I think just having just a base language, just as simple as we can, using nature as a guide, is a way for humanity to really level up.
And we know how to program reality. Like if we know we need a catalyst to do this or do something else, then we know where to put this transform logic. We know how to write programs. We know how to write programs that are understandable because everyone's learning, the same thing, the same logic. And one reason that I know that the photons are really good, for transmitting messages is we have something predictable on the other side. If you know what you are and you're sending a message and you know what library is running on the other side, that saves a lot. When we're using JSON, for example, to send messages, JSON's very popular, but it loses information. It doesn't have class information. There it just has fields and values. And it's transmitting, with these fields and values, and we're losing information. And it's because we don't know what's on the other side, what library you're using. But if we know that physics is running on the other side, then we can assume, I'm not sure if I'm explaining it right, but
the entire language goes along for free.
The entire language goes along for free, and we don't need all these packages to do translation and transformations because the same library that I'm using here is being used there because all software is engineered and built on top of the same
universal
library. Yeah. I think that even though I've been focused on a different problem, they match really well.
Oh yeah.
Well, there's going to be a computational equivalence. Like just even what you said in the past hour, I'm just like, damn. It makes a lot of sense.
You're trying to imagine the best connective structure logically, right? So you can do the logic stuff with it. And connective structure is exactly the opposite of decomposition structure, which is what I've been imagining.
Right. It's like starting from these particles down, like I believe they're going to fit together. I know that I have to get rid of the hardened particles because the universe isn't rigid. There are no hardened particles. But I think with the math, we can do that. And I have some ideas on how to program it. And there are a lot of things that other people can help on. Like,
Looks like it's about time to go.
All right. Well, I think we're done.
No, that was good, man. Good show.
Fantastic. All right. One more.